So, hello everyone. We'll continue the discussions from where we had left off last time. So, in the last class, we had left off at this 416C, and we were able to make this circle called the Mohr circle with one of the diameters is xy. The xy, if you recall, was the diameter which was formed when theta was equal to 0 degrees. And then using the other diameter, which is x dash y dash, and this x dash y dash was formed by essentially making this particular diameter. Okay, so this exact diameter has been taken out over here. Okay, so that's where we had left, and obviously in the x dash and y dash situation there was no requirement for theta to be 0 degrees, and that's why it was called the transformed, we would call it as the transformed stress components, and clearly x and y is the original untransformed stress components. Okay, so that's how you can see this diagram C 4.16C. Okay, so we'll continue with the discussions given in the textbook ahead. So this provides a convenient representation of the stress transformation equation. So this circle which you see provides a convenient representation for these equations which you have, these three, 1, 2, 3. And a set of stress components with respect to the xy axis is used to establish the xy diameter. Then the stress components with respect to any rotated x dash y dash axis can be determined to find the corresponding x dash y dash diameter. The manner in which the circle is constructed and used is summarized in a step-by-step list in the following paragraph. We'll definitely discuss this just because it's extremely important. And in order to follow these steps efficiently, it is necessary to understand clearly how stress components acting in a physical body are represented in the Mohr circle diagram. So the diagram is constructed, as you know, is in a stress plane. So this sigma and tau, this is called a stress plane. Okay, and just like because they have the stresses on the x and the y axis, abscissa and the ordinate. With the normal sigma plotted horizontally and the shear stress tau plotted vertically. For normal stress, tension is positive and is plotted to the right of the origin of this stress plane. So tension is positive. That is the convention which we follow in mechanical engineering. Okay, many of your colleagues in civil engineering or especially in geotechnical engineering, they have this convention that compression is positive, and they have reasons to believe that because most of the rocks buried deep inside the earth are actually under compression. Okay, so it is natural for them to take that compression as a positive sign. But we in mechanical engineering or even aerospace engineering for that matter, we undertake tension as a positive direction. Okay, so for normal stress, tension is positive and is plotted on the right of the origin of the stress plane. So if you are somewhere on the right side for normal, it means you are giving a positive force, which is tension. Compression is negative, so compression is over here for the normal stress, and that's how the tension is there. Okay. For the shear, the sign convention is complicated by the fact that we must distinguish between x and y ends of the diameter. Okay, so the positive shear tau xy is plotted downward at x and upward at y. Okay, look at this. Here you had this upward and here you have this downward. So there is definitely some level of confusion. And just to make it easier, we'll see it in certain examples below perhaps. Okay, fine. So the steps is what we'll be considering right now. You have, how do you draw this essentially? Okay, this is the steps which you must consider. So these are the figures which we'll keep in mind. Okay, so you have sigma x, sigma y and tau xy with respect to the xy axis at point O, okay, which is there in figure 415. So this is something which you already have. You can represent the state of stress at O by rectangular element in figure 417a. So if you look at 417a, you have sigma x, you have sigma y, you have tau xy. Okay, so that's what 17a is. Now to construct Mohr circle in 417b, okay, you have to proceed in a way which is described below. Use the sign convention of the stress component just given. We locate the point x with coordinates sigma x and tau xy, and the point y with coordinates sigma y and sigma y and tau xy. Okay, so then this is the x you locate with coordinates x sigma x, okay, and tau xy, this one. This is just trying to correspond to this place, okay. So you have sigma x and tau xy giving you this point, and similarly the point y, which is the other end of the diameter, is given by sigma y and tau xy. So that is given by sigma y and tau xy. Okay, that's how you have done this. Okay, that's how you have basically drawn xy, which is the diameter in the original configuration. Now you join, once you have two points, you can join them, and with a straight line, you would know that straight line, and then you have to see the intersection of this straight line with the sigma axis. Okay, that part also you can do easily. You have basically two lines and you want to find where it intersects. So that part is C, okay, and that abscissa of C is sigma x plus sigma y by 2. So this particular coordinate C is equal to sigma x plus sigma y by 2. Okay. So this you can easily find by taking the intersection for this one. So for tau equal to 0, you should be able to find it very clearly. Okay. Now with C as a center and xy, it is clearly possible for you to find the radius of this circle. Okay, you can draw the circle. Okay, and once you have constructed this circle, once the circle has been constructed, it may be used to determine the stress component sigma x dash, sigma y dash and tau xy dash shown in figure 4.17d. These stress components apply the same physical point O in the body but are in respect to the axis x dash y dash, which make an angle theta with the original axis. So this is how x dash y dash are. They make an angle theta, and you want to find the stress components in this new coordinate system. Okay, that's what the purpose is. So you have created a circle. You want to now, using this circle, you want to find what the value of sigma x dash sigma y dash will be. Okay, so let's see how that comes out. Okay, how does that comes out in practice when you really want to draw it. So let's take an example over here. You consider, so this is this is example, which one is this? It is example 4.1. Okay, example 4.1 over here. Okay, so you have the thin sheet, again thin sheet required because you have to have a plane stress conditions. We have already discussed earlier what a plane stress condition is, approximation is, and so the stress components are with respect to xy axis, as is given as 418a. So look at 418a. Okay, you have sigma x, which is this, you have sigma y, which is this, and you have tau xy, which is this. Okay, so these things are given to us, and we must find what is sigma a, sigma b, and I think tau ab, if I am not wrong. Okay, so you want to find all these three things, and you can see that the angle between this, so this coordinate system has been rotated by 45 degree. This has gone up by 45 degree, this has also gone up by 45 degrees. Okay, so that's the objective, and I mean we'll use the same ideas which we have done before. Okay, so sigma x, remember what was sigma x? I mean you can always look at 417 figure. Okay, you can go through these steps one by one. So first of all you have to draw the Mohr circle. Okay, so for that you'll need point x. Point x, if you remember, is sigma x abscissa, this one. Okay, and tau xy as the ordinate. So that's how you point. So this must be what, 110, and this must be 450. Okay, so I think there is an error again in your textbook. I think they have wrongly taken out the values. My guess is that it's not actually 450 but 40. Okay, so I think you can make this correction. This doesn't seem to be 450, it's 40. Okay, mega Newton. Okay, so let's that be a correction. Okay, so with this correction you should, so I'll just do it like this. Sorry. Okay, so once this is done you can find the x. Okay, and similarly you have to go 40 up over here and then 50 on this side. That would give you a y. So you have this now, which gives you the xy diameter, and then with this you are able to draw this circle. Okay, that's the first thing. Now what you do, you have to find the center of your circle, which again is not very hard. I mean it will just be the midpoint of this diameter, and it will be equal to sigma x plus sigma y by 2. Okay, so what is sigma x? We just write sigma x is equal to 110. I'm not writing the units just so that it takes less space, and then you have 50. So sigma x plus sigma y by 2 would be 80, and that's how you have the center of the circle over here. Okay, and it will lie on the sigma axis, so there's no point in trying to find tau, which will be 0 over here. Okay, so the center of the circle is found. Now you have to find the x dash y dash angle. x dash y dash line. Okay, x dash y dash line. Yeah. So how do you go about doing that? You see the angle which this forms and which this forms is separated by this 2 theta. Okay, for us theta is 45 degrees, so 2 theta will be equal to 90 degrees. Okay, and with your basic geometry you can easily do a few things about this. Okay, so you want to find this x dash y dash or AB in this case. Okay, so let's call the AB line. How do you find the AB line? You already, so assume the equation of this line is y equal to m1x plus c1. Okay, this particular line, which is xy, can be equal to y is equal to m2x plus c2. Okay, this is known. Okay, you already know what this equation is exactly. This is unknown, like m1 and c1 is not known, but there is definitely something known, that this passes through C, which is the center of this circle, and that is actually 80,0. Okay, so one unknown will be solved out of this, so you require one more condition, and that condition will come from the fact that these two lines are aligned at 90 degrees from each other. So m1 into m2 should be equal to -1. So with this condition and this condition, you should be able to find this equation. Okay, and that's like one way to go about it. And then you can always see the intersection of the circle with this line of AB, and then you will get the coordinates of A and B. That is one method. Okay, and you can always have the other method, in which has been discussed before. So you are free to use any method which works for you. Okay, so this method which I have just discussed is slightly lengthier because it solves you trying to find the values, but I mean, if you are able to, that's no problem at all. Okay, okay, so that's how you would find sigma A, sigma B and tau AB. So you can always also check the solution in your solutions in your textbook. Okay, so you would have a similar sort of a situation. So let's also discuss about the directions right now. Okay, so let's say that you have found out that sigma A is equal to this value, 120 mn by meter square. Sigma B is equal to what, 40. I'm just taking these numbers from your textbook. Okay. So in your textbook, the way they have done this problem is again quite simple. What they have done is they have taken the theta 1 angle, this angle 2 theta 1, as tan of 2 theta 1 is equal to what, 40 divided by 30. Okay, this triangle. This is 40, this is 30, so tan 2 theta 1 is 40 by 30, so that gives you what 2 theta 1 is. Okay, 2 theta 1 is known, that comes out to be 53.2 degrees, and then the radius of this circle can be easily found out as 30 square plus So I mean, this dimension is known, this dimension is known, and this is 90 degree. So this hypotenuse can be found out by this value. That comes out to be 50 mn. One of the things is, please write the units wherever you see them. I mean, because this is no longer an I mean, even in the usual geometry, the distances have units. So here, these dimensions, because now your x and y axis are not coordinates, they are actually stress. So everything which you calculate is should have the units of stress. Okay. So sigma A, again, I mean, with this R, what you can do, sigma A can be found out. I'll just cut out all this. So sigma A is over here. So that value is equal to clearly, so sigma A, you must come this far, and this far is equal to 80. Okay, so that is 80 plus, you must have this value. Okay, that is 50 cos 90 degree minus 53.2 degrees. Okay, so essentially you are looking for this angle. This is 90 minus 53.2 degrees. So that will be this R, which was 50. Okay, R was 50, and cos this angle, meaning the projection over here. So you get this distance. That gives you a sigma A. Similarly, you will get a sigma B, which would be what? You come to this distance 80 and then subtract out certain part of it. Okay, so it would be 80 minus this value. Okay, so that would be 80 minus 50 cos of 90 minus 53.2 degrees, and that comes out to be 120 and 140 respectively. Okay, so sigma A and sigma B are found out, and this method is fine. The earlier method which I had told was sort of more linear. Okay, anything works, whatever works for you is okay. Fine, so let's move ahead now. Now you can use the two methods, that is, use scale diagram and find the values whichever works for you. Now you have to use this Mohr circle to represent the normal stress and shear stress, then rotate the diameter line to twice the angle to find the stress components in the differently oriented plane. Now because point A lies above the sigma axis and point B below, okay, that's something which is coming out. So this observation that point A lies above the sigma axis and point below the sigma axis will come out because after you have rotated it by 90 degrees. Okay, so after you have rotated this by 90 degrees, you will come to this conclusion, not before that. Okay, maybe it could have been rotated by a very small angle, then this would not be true. Okay, so now the shear stress tau AB is negative. Okay, so tau AB, see, tau AB, when it was coming over here, this was positive. Okay, this was also positive. But if this x and x dash has now crossed on above, hence this time we know that tau AB or tau x dash y dash will be negative. So this is a minus 50 sine 90 minus 53.2 degrees. Okay, so I hope this point is very clear. How do you know the shear stress value? So if this, your x dash is actually after rotation, if x dash is below the tau equal to 0 line, then it's a positive value, and the same will apply over here. I mean, if whatever it goes up, it will go down over here. So this should go up, should remain up there. but after rotation, if this x dash lies somewhere over here, then it means that the value is negative. Okay, this was the point which was discussed in the method. So it was perhaps easier to see in this example rather than the method itself. Okay, so you've got tau AB as well, and these stress components are shown acting in their current directions on the faces of the inclined crack as inclined element in 4.18C. So 4.18C is this. So you have to put sigma A as 120, sigma B as 40, and sigma AB is 30, but you look at this arrow. Okay, this shows that it's a negative value. So now we don't write it as minus 30 in the figure. Okay, or the other way is you just write like this and then put a minus 30, but not forget the units. This is also okay, the arrow pointing it like this, or this is also okay. Fine. So this is one thing which you have seen, and I think right now is a good time to really see why you would want to study all this. In the sense, I don't mean the discipline of mechanical engineering, or for that matter the subject of solid mechanics, but the very fact that why would you want to rotate your coordinate systems and so on, and why is it that a fascinating idea? Why was I so excited that if you have the state of stress defined by these 9 or 6 numbers, you can find those values at any orientation of the plane? Why was it so important? So let me give you one example of a solid. So think of this as your one of the solids, okay, and maybe like a wood, okay, from the bark of a tree, and then this is how you can do a compression test or a tension test in the opposite direction. You just push it, and then you measure the forces which you are applying, and then you can get on with doing some sort of a mechanical analysis. Now normally materials like the wood, or for example bone is another good example. Okay, the structure of a bone is that it has these fibers at a certain angle. Okay, and same would happen with a wood as well. Now in a case like this, if your coordinate system is x and y, okay, you will be, say, if this is your point of interest in the center, you will clearly be able to define sigma x, sigma y, tau x, y, and so on. But for materials of this nature, okay, which have these orientations aligned, say, at an angle theta, okay, it so happens that these are very strong in this direction along these fibers, both your bone and the wood, and in that case it's a good idea and a good practice, and actually very makes calculations analysis easier to convert this into this x dash y dash system, so as to align the coordinates. So originally the coordinate system is not aligned, okay, but right now it is aligned to this. So and then you can say, if you have the stress somehow measured over here, you can find the stress measured along the orientation of these fibers, and then you can better predict whether the wood or the bone will break or not, okay, because it is stronger in that direction. So this is one classic example. This property is called anisotropy. Okay, so we won't be going into a lot of detail in this course. Perhaps very later in the course, if time permits and if you are still enthusiastic, we'll come back to this. But the idea is that the behavior is different along different directions. So it's different along this direction, it's different along this direction. As I've said, it is much stronger along the direction of the fibers. So we will see that when you try to break it, okay, it will be much more harder to break in these directions compared to this direction. Okay, so that's the reason why you would want to transform the stress components at any direction. Okay, and it doesn't actually end there. I mean, if this is your bone, okay, human bone which you have, and well, I mean, you always know the fiber direction. You can always look at it and find the fiber direction, and you can find, well, it's strongest in this direction. So let me find the values of stress it can take in this direction, but it will also be weakest in the other direction, which is this one. Okay, so many a times this analysis is needed to keep on trying along which direction you get the maximum and the minimum value, and you will see that that is coming from a side where you try to study failure in a material. Okay, all this will be much better dealt to you in your course in machine design or design of machine elements, where you study all these failure theories, and for all of those failure theories you will require this conversion which you are learning now in this course. That is will not be taught there in that course. My guess is that it will be assumed that you already know how to draw the Mohr circle and make all these transformations. Okay, so since I think you have understood why it's important, so let's move ahead. Okay, so there is a sort of an important combination, okay, as so called, that is represented by the diameter which is aligned with the normal stress axis. Let's see that. Let's see this 4.19. Okay, 4.19. So the end points of this diameter are designated 1 and 2. So let's just consider a case, okay, where you have this sort of a situation. Okay, you have a sigma, you have tau, you have x, you have y. You have already done that part, and the end points of this diameter, this point on your circle, okay, is 1, and this point on your circle is 2, and please call them as 1 and 2 as they are. Okay, they will be important at some point where you see them. So this value can be easily said to be what? Sigma 1. This value can be said to be sigma 2. Okay, so these are normal stresses, clearly, because they lie on the sigma axis. And one of the other thing is that there is no shear stress, right? Tau is 0 at both of these points. So the coordinate actually is sigma 1 comma 0 and sigma 2 comma 0. Say somewhere over here the same is not true. Here you will have both sigma and tau, right? So for 1 and 2 you have this sigma 1 and sigma 2, which are normal stresses. Shear stress is common. Sigma 1, if you note, is the maximum possible normal stress component. Sigma 1 is the maximum possible normal stress component. Okay, and sigma 2 by the same logic is the minimum possible. Okay, so sigma 1 and sigma 2 are called something as the principal stresses, and sigma and 1 and 2 are called the principal axis of stress. Okay, so in terms of the abscissa C of the center of the circle, sigma 1 will be equal to C plus R, okay, and sigma 2 will be equal to C minus R. Okay, so this is important, and first of all I'll tell you why. I mean, this is not something new. You may have learned in your maths course of linear algebra something called about the eigenvalues, and for that I will have to briefly take you on a small tour of what these things are. Okay, so assume that you have this coordinate system x and y. Okay, sorry, it should be I and j. Okay, j cap. You consider a point, say 2i plus 3j, 2i plus 3j, this point. Now if you look at this vector, okay, it has its component on both the directions, right? In the x direction, in the I direction, it has a value of 2. In the y, in the j direction, it has a value of 3. So it has its sort of value spread out along both the axes. Now if I ask you, what is that way through which I can align the entire magnitude of this vector along one of the axes? Okay, you would say that, well, I can have a rotated axis in this form, right? In this way, this entire vector lies along the this I dash, okay, I dash, j dash cap, and so on. Okay, the other way is also to rotate this by this way, and then you would have your I somewhere over like here. So either way you can do this, and you will have this entire vector lie along one direction and not the other direction. So this actually two values, particular rotation allows entire vector to come along one direction and none along the other. Okay, I mean, if there is some part of it which is coming along the other direction, it doesn't really help, because that was anyways happening even in this blue coordinate system, right? So we want to rotate it in a way that the entire vector comes along this one axis, and there were two possibilities as you have seen. So there is this rotation which has happened, and through which this is possible. Now this was the last visualization which I could have shown you for this fact, but I really want you to see this. You have a 1 2 say 3 4, a 2 by 2 matrix, and you want it to undergo a rotation. Okay, the coordinate system undergoes a rotation. Under what rotation that should happen, that you get a value only along the principal directions, which is this sigma xx and sigma yy, but tau xy is 0. Okay, just like it happened in the previous case. This is what we are trying to question over here, and those 2 points are, so this will be actually equal to sigma 1 and this will be equal to sigma 2. So this is what sigma 1 and sigma 2. The entire stress components have been distributed along only these 2 directions, and on the shear direction there is nothing, 0. That's why tau xy is 0. Okay, so this is the same as your eigenvalue which you had studied in your linear algebra course. You should definitely go back and see the theory behind it. Okay, there is something called a characteristic equation. Okay, and then you have this eigenvalues and eigenvectors. So this is that. So sigma 1 is the eigenvalue. Okay, sigma 1 and sigma 2, they are the principal values, and what they do is they don't allow component distress sigma x, sigma y, tau xy, tau xy. This has a certain rotation theta. Okay, and what you get is sigma x dash, sigma y dash, sigma x, sorry, tau xy dash, okay, x dash y dash, tau x dash y dash. Now what should happen that this becomes 0, and this then is called sigma 1, and this then is called sigma 2. This is what we are referring to over here. So this concept is very aggressively used in many failure theories which you will be learning in your machine design course. Okay, how this sigma, most of the actually failure theories are built on sigma 1, sigma 2 and sigma 3 in the 3-dimensional cases. Okay, and this is how it is used over there. So once you are done with that part in machine design, I request you to come back to this theory and see again and read it again in light of what you have learned in that course. Okay, so this is one small discussion which had to happen over here. And so in one of the other possibilities, let me just remove this part. Okay, one of the other possibilities of 419A is this DE. Okay, this is also an interesting diameter. Like 1, 2 is an interesting diameter, DE is also an interesting diameter. What does this tells you? It tells you the at this diameter, okay, the normal stresses are equal. Okay, so sigma x dash will be equal to sigma y dash, and the magnitude of the shear stress is maximum. So tau x y dash x dash y dash is maximum. You can see that, right? D, it will give you the maximum value. So this is also another interesting case, and this, in this case, obviously this R is your tau max, and sigma D is equal to sigma E equal to C. Okay, this value. D is the axis of maximum shear. This is the axis of maximum shear. This is the principal axis. Okay, and these are the principal values. So if you can easily see that the axis of maximum shear, the angle between 1, 2 and DE is 90 degrees. Hence it requires a rotation of 45 degrees. Okay, so that is one other point which may be made over here. Okay, so you have a case of this example 4.2 in your textbook, and again, just like the previous times, you have a situation given to you. You have the same example 4.1, and now you are supposed to find the principal axis and the principal stresses and the maximum shear. So basically you start off with this diagram, okay, what you had derived over here. Okay, so you have already found sigma x dash, sigma y dash and so on, and the state of stress is the same. You want to find what the principal values are. So sigma 1 you can just write as C plus R, and sigma 2 as C minus R, and similarly tau max will be R, okay, up with the appropriate units. So this is how this discussion has gone around until now. And one other thing which I would request you is that don't remember any of the formulas over here. You will never be given a situation that you can just have sigma xy, sigma x dash and sigma y dash directly written from a formula. That will never be there in any form for that matter. Okay, so there's no need to remember the formula. What you have to really go through and very carefully is about the steps which undergo through, and you should try to do as many questions as you can from this topic. Okay, only that, because many times the sign goes wrong, the formulas, I mean, there is some error in calculating the angle and there's some confusion, and you have to merge all this knowledge with two courses, as I have said. One is machine design, I mean, it may have some other name, but it's essentially designing of machine elements, and the other is your linear algebra. So what this course, so linear algebra would have done all this. I mean, they may have done it for a much larger system. So you only need to worry about a 2x2 system. Okay. So they normally work in n dimensional systems, which for us doesn't really matter much. I mean, 3 dimensions is at max what you would need to survive this world. So I think that's fine enough. Okay, so linear algebra had done all this mathematically. This course has given you a physical interpretation of how that knowledge is applied. You must read this in light of both of these two courses, and once you know this physical understanding, you will see how failure theories are applied in machine design course. So there is a proper link between linear algebra, mechanics of solid, and machine design course. So I request you to please go through them as the time comes up. Okay, fine. So what we'll do now is we'll cut the our study today, and in the next class, whenever that happens, we'll be continuing with the next topic about this, which is the Mohr circle representation of a general state of stress. Okay. The reason I'm not starting is because there are only a couple of minutes left for this class, and it will take slightly longer to get there. Okay, so we'll do that. Thank you, and see you in the next class.